going to continue the second part of discussions about what a limit is. And before we do, let's start with this screen where we just kind of review what we talked about in the last piece of the lesson, and that is the idea of how to find a limit and what a limit is. So remember, in calculus we're being asked two questions. Where is our function headed and how fast is it getting there? And the limit answers the question of where is it headed. So if we want to know where somebody's hanging out, if they're around milepost 2, then we would go to where x is 2 and see where our function is headed when we approach that point, either from the left or from the right. And if we approach from the left and the right and we approach the same place, then we would say that the limit of that function is that place we are approaching. Now, when we talk about the limit of a function, that does not mean that there has to be a point on that function at that area. It is where are we approaching. So we're not actually getting there, but where are we hanging out. And typically, to find the limit of a function, we can simply plug in or find f of c. So if we want to know what the limit is as we get really close to 4, to x is 4, then we would plug in 4 to the function. And that works great except in 3 situations, maybe even 4. Is there a gap or a break in the function? Is there a hole in the function? Is there an asymptote? Or is there no function at all? And we'll look at those 3 on the next screen as a review. Remember, I said the approach from the left has to be the approach from the right. And we talked about the fact that the limit of a constant is a constant because the function value is always the same. So let's look at the 3 situations when there are possibly no limits, or not necessarily that there are no limits, but that we can't find it by plugging in. So the first example is an example where our function has a 0 in the denominator. So if I plug a 0 in here and here, I'm going to get a 0 in the denominator, which is undefined, which means there's not a function value at x is 0, but that doesn't mean that there is not a limit. This one actually has a hole in it. If you look at the graph of this, at x equals 0, there is a hole. And the way that we would be able to work that out is that we would have to take the top here and clean it all up, multiply it out, and then divide everything by x. And on the next slide we're actually going to do example where we're able to get rid of a piece, and that indicates that there's a hole. So substitution will not work there. What we have to do is factor and reduce and see if we can find the limit that way. The second example here, as x approaches -2, if you look at the graph of this, starts at x is 2 and goes like this. So there is no function to the left of +2, and if there is no function, there can be no limit. And the last example is where we actually have an asymptote. Remember, an asymptote is a vertical line that your function cannot cross at all. And so this one does not have a limit because it approaches the asymptote from different directions and goes to infinity. So we talked about that a bit in our last lesson, but I just wanted to refresh those. And now what I want to do is actually revisit the substitution method, and then there's a little bit of a method we call trickery. So the idea behind the substitution method is it helps us to answer the question on whether or not we have a hole or an asymptote. If our graph has a hole, then we can approach that hole from the left and the right, and therefore, so we have a hole, we can have a limit. That does not mean there has to be a function value. If our graph approaches an asymptote, they might approach in the same direction or they might approach that asymptote in different directions, and so we typically do not have limits there. Some would argue if they approach, they both approach in the same direction, you might say that that limit is positive infinity. That doesn't really make much sense to say your limit is positive infinity, but it does tell you where the graph is going. So, how do you determine whether you have a hole or an asymptote? What you do first is you factor. So we're going to factor this graph. And if you need help on factoring, there are some videos. If you check under tips and tutorials in Blackboard, you'll find some videos that can help you review factoring. And when we do, we are able to eliminate one piece of our problem, and that is x minus 1. And we're left with x plus 2 over x. So here's the situation. If x equals 0, our graph is undefined, and that's not removable. We can't get rid of that x in the denominator. This is an asymptote. So if the problem in the denominator cannot be removed, it's an asymptote. And if x equals 1, we were actually able to remove that problem right there, and so that makes it a hole. So you would expect to, if you look at the graph, you would, if you look at the graph of the original, oops, there should be a hole right there. Okay, the original graph would have this hole, but we can find the limit as we approach that point, and that is x equals 1. And there is that asymptote at x equals 0. So if I asked you what the limit was as x went to 0, that would be no limit, because they're going in opposite directions. But if I ask you for x equals 1, what we can do is take x equals 1, plug it in to x plus 2 over x, and we get that the limit is 3 over 1, or 3. What that means is this y value right here is 3, and we approach the y value of 3 from both the left and the right, but our function would never have a point at 1, 3. Okay? So this function here and this original function are very, very similar. What the one thing they don't have in common is the point at 1, 3. So when we try to find the limit of something, the first thing we do is we plug it in. If that doesn't work, another thing we try is determining if it's a hole or asymptote by eliminating the problem. We also look at the graph. Remember, we can determine limits by looking at the graph and getting a feel for where it's going. Okay. Sometimes we have to play trickery, and that is, can we do something legal to the function so that we just change how it looks versus changing its value. And so remember, when you have a fraction, as long as what you do to the top you do to the bottom, you haven't changed the value of that function in general. So this one, and this is going to be weird, and I know it is, we're not going to see this very often. But when you have things like square roots, if you remember back a long time ago, you learned something on how to get rid of square roots. And so we can't cancel the h's here because that top stuff is in a square root. What we can do is we can multiply the top and bottom of this fraction by the conjugate of that binomial with all the square roots. And so we're changing how this fraction looks a little bit. And when we multiply all of that out, remember when you multiply by conjugates, the middle terms cancel, and anything times itself is itself squared. So we have the square root of 2 plus h squared, which is 2 plus h. And then we have minus 2, and then all over h and all of this stuff. Okay, and now up top we just have h over h, square root of 2 plus h plus square root of 2. I lost the square root of 2 somehow back up there. The h's cancel. We're left with 1 over the square root of 2 plus h plus the square root of 2. Now I can plug in 0, and when I plug a 0 in right there for h, I get 1 over the square root of 2 plus square root of 2, which is 2 square roots of 2. And so this is my limit. So if your fraction just looks really weird, it may be possible, especially if you look at the graph and it looks like you have a limit, then to find that limit you may have to do some trickery, and one of those trickeries is often using a conjugate. The next two slides in your packet are simply a list of rules that we don't need to go over piece by piece, because basically what we've learned incorporates these. The whole idea is, if you've got a function with a bunch of pieces, you can find the limit of each piece and then put them together, or you can find the limit of the whole thing. You can substitute into the whole thing. So now the one that you might pay attention to here is number 11. That says the limit of b to the f of x. Notice the function is up in the, this is a exponential, the function's up in the power. So you're really taking the limit of a function because the base is not changing. It's the power that's going to control things. Same with the log. You're taking the limit of the function because the log is not changing. So let's put all this together as a review and see how to find the limits. So the first example is our first step would be to try to plug it in. And so if we plug in -1, we would get 3 times -3, and so it looks like our limit should be -9. So if you were to graph that function in your calculator, and please take the opportunity to graph a couple of these, if you trace your calculator cursor on the graph until you get close to -1, you should be approaching -9. The next one, when you have a denominator, the first thing you want to do is see if there's any problems with plugging in. But in this case, we can plug a 2 into the bottom. And so we can simply plug in 2 squared plus 5 times 2 plus 6 over 2 plus 2. So we get 4 plus 10 plus 6 over 4, which looks like 20 over 4, which I believe is 5. So the limit, again, if I were to put this in the calculator, make sure when you put it in the calculator the top is in parentheses and the bottom is in parentheses, and that you, as you trace that as, now be careful, it says as y goes to 2, but you have to treat that as x goes to 2. So put this in your calculator using all the x's, trace it to 2, and you should be hovering around 5. The next one, if we quickly look at the denominator and see that if we plug a 1 in there, that 1 is going to cause the denominator to be 0. So that immediately tells us don't bother to plug it in. Let's see if we can factor and get rid of something. And so up top, this factors to t minus 2 and t minus 1. And down bottom, t plus 2, t minus 1, and these reduce out. So what does that tell us? We've got an issue at t equals -2. We had an issue at t equals 1. That means there's a hole here, and I don't think I need that w. I'm just going to scribble that out. And t equals -2, remember that means we have an asymptote. Okay? But we're not worried about at -2, we're worried about at 1. And so what we can do is take our new, what I like to call our helper function. Remember that the graph of that is similar to the graph of the original, simply with having a hole or not a hole in it. And now we can plug 1 into this. So 1 minus 2 over 1 plus 2, which will equal negative 1/3. So if you graph this original function and you approach t equals 1, you should get really close to negative 1/3, but there should be a hole there. All right, and so let's start with a discussion on this last problem. The limit as x goes to 0 of the 2 plus x cubed plus 8 over x. One thing you could try to see if you could get rid of x is to multiply all that stuff out at the top and add 8 to it, and then see if you can divide by x. But because that's not a minus 8, you're going to have that constant on the end no matter what, and you can't divide that by x. So we're not going to be able to remove the x, which indicates we have an asymptote. And if you take the time to put this in your calculator, and again, put it in your calculator with parentheses around especially the top, and when you graph that, and you kind of have to mess with your window a little bit, make it kind of like your x is from negative 10 to 10, but your y is from like negative 50 to 50, you see a graph that kind of goes like that, and then up here a graph that goes like that. And so what's happening is we've got this going to negative infinity and this going to positive infinity at x equals 0. So we do not have a limit here because we have a vertical asymptote. So the graphs can be very helpful. If on this graph here I asked you for the limit as x goes to 2, well, that's kind of the same case if that were 2. Is that from the left I'm going down, from the right I'm going up, so there would be no limit. And then on this other graph I could ask different questions. What if this were 1 and this were 2? And I asked for the limit as x went to 1. Well, as I approach 1 from the left, it looks like I'm going to 0. So the limit as x approaches 1 from the left is 0. Let's say that this is 5. But as I approach 1 from the right, the limit as x approaches, I'm sorry, that should be underneath, as x approaches 1 from the right is equal to 5. And so we're approaching two different places, so that would have no true limit. But if I ask as x approaches 2, so this one was no limit, the limit as x approaches 2, from the left I'm approaching 5, from the right I'm approaching 5, so I'm approaching 5 from both sides, so my limit is 5. So 3 or 4 basic ways to find limits. Number 1, can you plug it in? Number 2, if you can't plug it in right away, can you remove the problem and then plug it into that little helper equation? Number 3, if you can't remove anything, chances are you have an asymptote and you need to take a peek at the graph. And number 4, remember sometimes that we have to trick things. So that's how we find basic limits. Now let's look at what if we want to talk about infinity. In other words, if we asked what is the limit of a function as x approaches infinity, what is that really asking? What are we trying to find out? Well, what we're trying to find out is if I get on that function and I keep walking forever and ever and ever and ever, where am I going towards? Where can you expect to find me a million years down the road? So as we travel to infinity, we're asking, what is my graph doing way down at the right if we're talking about positive infinity, or way down to the left if we're talking about negative infinity? Well, there are only two functions that we can truly get a grasp on way down at the ends. Because think about it. If your graph does something like this, then way down here, my graph is going up, up, up. And way down here, my graph is also going up, up, up. Or it could be going down, down, down. So a lot of graphs keep getting bigger, 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 or more negative, more negative, more negative down at the ends. But as I mentioned, there are two functions that we can do. One of them is this. And do you remember what that's called? That's your constant function. And no matter how long you walk, if you keep on walking, either direction, we know where you are because you're on that y constant the entire time. So the limit as x approaches infinity, or I could have it approaching negative infinity, of a constant is in fact that constant. I know where you are every time. The other graph that we can get a grasp on is a graph that keeps getting closer and closer to the x-axis but never crosses. And so it's a graph that looks like this, that no matter whether I'm going to negative infinity or positive infinity, those graphs are getting really, really, really close to y equals 0. Remember, this is y equals 0. So that graph is 1 over x. And think about taking the number 1 and dividing it by a number that's getting bigger and bigger and bigger. So 1 divided by 4, if you take one cookie and share it with 4 people, you get a little bit of cookie. Take one cookie, share it with 100 people, everybody gets something, but you get a lot less. Take one cookie and share it with 1,000 people. Everybody still gets some, but that crumb is getting so tiny you might not even taste it. So you're getting closer and closer to 0. So the limit as x approaches infinity of 1 over x is 0. So these are the two concepts that we can use when we want to find the limit as x approaches infinity. In other words, we're trying to control what is happening with our company in the future. Okay, do I know where my company is heading 100 years from now, 200 years from now, and so on? So we have two rules. One is the constant rule, and one is the inverse identity, because 1 over x is the inverse of x. Okay, and all the other properties for limits hold true, like the sum of the limits is still the limit, and so on. Okay. I asked in this slide, why doesn't identity work? Well, the identity, remember, is y equals x. So as x gets bigger and bigger and bigger, what happens to y? It also gets bigger and bigger and bigger. All right, let's put this to work. So here's our thing. The only things we can find limits of as we go to infinity are the constant function and 1 over x. So every one that we want to do, we have to trick the function into looking like one of those. Okay, so we either need to trick it by looking like a constant or by looking like 1 over x. And to do that, we divide each term by the highest degree in the denominator. And then we simplify it and we take the limit of each piece. So let's give that a shot. So here's a set of examples. Well, the first one we just did. The limit as x goes to infinity of 1 over x is 0. Again, you got to know that. And number 2, you have to, or don't forget, you can always look at your graph and just trace it forever down to the end and see. All right, the next one. Here's that rule we can use, and that is we can take the limit of 5 plus the limit of 1 over x. So those rules I were telling you about, it comes in handy here so we can take the limit of each piece. And these are the only two pieces we do know how to take the limit of. So the limit of a constant is the constant, so the limit of 5 is 5. And the limit of 1 over x, as x gets bigger and bigger and bigger, is 0. and so our total limit is 5. We would expect that this graph way down to the right is going to get closer and closer to 5. The next one, the limit of x as x approaches infinity of 4 over x squared. Well, let's think for a minute. If the limit of 1 over x is 0, then the limit of 4 over x would just mean instead of only having 1 cookie to share with 1,000 people, we have 4 cookies to share with 1,000 people. Well, your crumb's a little bigger, isn't it? And then when we have 4 cookies to share with 1,000,000 people, your crumbs are getting smaller. So our crumbs are still getting smaller. It's just that they're getting smaller at a slower rate. Or the other thing we could do is this, where we have the limit of 4 times 1 over x times 1 over x. That's another way to, we have the limit of that whole thing. It's another way to look at this problem, but I'd like for you to try to reason out what I was doing right here, where I just did the little arrow thing. If 1 over x, the limit of that is 0, then the limit of 4 over x has to be 0 because we just have a little bigger crumb to start with. And the limit of 4 over x squared also has to be 0 because you're sharing 4 cookies with x squared people. So the number of people you're sharing with is getting huge fast. So our crumbs are getting smaller really fast. But if you don't like to think about it in that way, then just go with breaking it into pieces. And so we do the limit of 4 times the limit of 1 over x times the limit of 1 over x. And the limit of 1 over x is 0, and 0 times anything is 0. So all of these arguments are why it's 0. Now, the next one we can't just break into pieces because we have that entire thing on top divided by that entire thing on bottom. So this is where we're going to do that little trick, and that is that we're going to divide everything by the highest variable in the denominator, which was x to the first. So we're going to divide everything by x. And so up top we have 3x minus 6 over 4 minus 8 over x. And now we're going to take the limit of this whole thing as we approach infinity. All right? So let's think about this. There's a couple of them that are easy. I'm going to leave the hard one to last. The limit of 6 is 6 because the limit of a constant is 6. The limit of 4 is 4 because the limit of a constant is 4. The limit of 8 over x as x goes to infinity is 0 because 8 cookies shared with millions of people, the crumbs are getting tiny. So that's the 1 over x argument. But we have the limit of 3x as x goes to as x goes to infinity. We haven't done that piece yet. So I've gotten everything else done, but I haven't gotten this. Well, what happens if x is getting bigger and bigger and bigger? What happens to 3 times that? Well, that's almost like saying 3 times infinity minus 6, and 4 minus 0 is 4. Well, 3 times infinity is just triple infinity. It's just huge. And whether or not you subtract 6 from it, it's still huge. And whether or not you divide it by 4, it's still getting bigger. It's just slowing it down a bit. So we would say that this limit is infinite. In other words, it's growing in the positive direction without bound, or you could even justify saying no limit. And so please, when you're working in MATLAB, take a look at their examples there and see if they're looking for you to say infinite limit or no limit based on the wording. So that's how we deal with finding limits of infinity. Now, let's take a look again at that graph to answer these two questions. If you graph 1 over x in your calculator, it looks like this. And so this first question here is, as I approach 0 from the left, that my limit is going to negative infinity. And as I approach 0 from the right, my limit is approaching positive infinity. So I think I would be happy on that last example we were doing for us to say positive infinity, because it does at least give us some information on how the graph is going. Okay, so when it comes down to a test or us having discussions, if we can give information about our graph, it's going to positive infinity, that tells me a lot more than you just saying there's no limit. So I'm not really going to be a fan of that, but if MATLAB needs it, then MATLAB needs it. Okay, so limits tell us where our functions are going. We try to plug in first. If not, we look at the graph. If not, we look at substituting by getting rid of the problem by factoring. Sometimes we have to try trickery. And the two that we can find the limit of as we approach infinity are constants and 1 over x. And that's how we can find that. I'm going to stop there with our discussion on limits, and I'll pick up in our next little lesson with a short discussion on continuity. So please take a look for that in just a minute.